In today's lesson, we are going to be looking at measures of spread. So in the previous lesson, we looked at measures of central tendency, which talked about the middle value, the center of our data set. Now we're going to be looking at measures of spread, which is going to be different statistical measures that look at a different component or a different aspect of our data. So what are measures of spread? Well, measures of spread, they help us describe the variability in a data set. And variability is something we've talked about previously. It's something that we don't really want to occur, right? Because variability is how the data is spread out or how it varies. Right? And when we're talking about data, we would like it to not vary, all right? Because that's one of the things where we're looking at bias or looking at issues with the data, right? We want things to be consistent. Right, so we want to try to reduce the variability when we're collecting data or in our samples, and measures of spread will tell us how well of a job we did. Now there's three measures of spread that we're going to look at: range, interquartile range, standard deviation. Interquartile range and interquartile range we'll look at in a future lesson. We're going to focus primarily on standard deviation this lesson. Range is relatively straightforward, so we don't usually worry about that too much. For example, so range, easiest measure of spread, it's the difference between the maximum and the minimum, or the difference between the highest and the lowest data points. Right? Difference means subtract. So we're subtracting the lowest data point from the highest. And again, similar to the measures of central tendency, we can kind of misrepresent these values. So for example, our range, right? We might say our students come from a wide range of socioeconomic backgrounds. And when we look at the actual data, we find that yes, they do come from a wide variety, right? From low to high and everything in the middle. However, when you look at the actual number of students from those different backgrounds, you can see that it's kind of disproportionate and it's more high socioeconomic backgrounds that are in this class or in the school or wherever the comic is situated. Right, so the range can be misleading. Standard deviation. So standard deviation is going to be the main one we focus on today, and it contains two measures in one. It contains the variance and the standard deviation. So when we go through and we calculate standard deviation, we actually find the variance first. Right? And the variance is the average of the square distances that each data point lies from the mean. And standard deviation tells us the typical distance any given point is from the average, right? So it kind of gives us an idea of how far our a random point might be from the actual, from the average or from the mean. To fit completely, the data must fit a normal distribution, which we'll talk about in a little bit after. In terms of how it represents, but we find that most data does tend to fall in a normal distribution. So variance, again, can be misrepresented. So these results are a disaster. Sure, they look bad, but there's lots of variance. Don't rush to judgment, right? So we look at our data, we can see that yes, there is going to be high variance or high standard deviation because the data is spread out, right? We have that one outlier that's showing a great result. Right, so it might say, well, our data is very spread out. There's a lot of variability. It's not consistent. So even though our results might be terrible, well, there's lots of variability. So maybe there's issues there. But when we look at the actual results, it's just one value that's causing that variability, and the majority of the results are terrible. So our different formulas. So we will work through these. Now, we mentioned previously on measures of central tendency, we had two different formulas, one for population, one for sample. And those calculations or those situations carry over in measures of spread. And there is actual differences. So it's not just using different notation like the mu and x bar, right? It does actually come with different equations. Right, so we're trying to find the population or the standard deviation or variance for the population. These are the two formulas. Right, so we have our standard deviation or variance. Right? I believe maybe it's lowercase sigma. I'm not too sure what the Greek letter is, but basically what this is saying, and we're going to focus on standard deviation because we don't really use variance. But the standard deviation formula is the square root of the sum of each value minus the mean squared divided by the number of data points. All right, so we're seeing what is the average squared distance between the different, between each point and the mean, and then we square root it to find basically the average distance between each point and the mean. So basically how far away is each point from the average. Right, X represents each data point, mu is the population mean, and capital N is the number of data points. The sample standard deviation is very similar. It is the almost exact same formula, except instead of mu, we have X bar, right, representing the sample mean, not the population mean. And instead of it being N on the bottom, we have N minus 1. And we'll talk about that later when we look at an example looking at sample standard deviation. So we talked about the data having to fit into normal distributions when we're dealing with standard deviations. And essentially what that means, this is a normal distribution here. And what this is showing is where is the majority of data? Right? Where would our data points fall? Now here in the middle, this is our average, this is our mean. Right? So the middle of our normal distribution is our average, or 0. And along the bottom, these are representing 1 standard deviation, 2 standard deviation, 3 standard deviation. Right? So we can say this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. So basically what this is showing is what percentage of data is away from the mean or within a certain distance from the mean. So in the first part here, in our first part, this shaded area here, this is basically saying that 68% of the data, or 68% of our data that we collected, or whatever of the scenario, 68% of the data should fall or is within 1 standard deviation from the mean. And that's plus and minus. Because here we have 1 standard deviation. It should say plus 1, plus 2, plus 3. Here it's minus 1 standard deviation from the mean. So saying 68% will fall within 1 standard deviation of the mean, and again, the standard deviation is just a distance or a hypothetical or a metaphorical distance from the mean. When we move 2 standard deviations away, we find that we add 13.6% data on either end. So this is telling us that in 2 standard deviations away, there is 95% of the data. So 95% of the data is within 2 standard deviations from the mean. And then lastly, 3 standard deviations. The next section, we're adding 2.1% on either end. So this is essentially telling us, this is telling us down here that there's 99.4% of the data falls or is within 3 standard deviations. So basically, the majority of our data should be between 3 standard deviations plus or minus from the mean, right? And again, the standard deviation, the measurement is just going to be a metaphorical distance or a value. Right? And then the 0.6%, that is everything that's beyond our data. Right? So that's above the 3% or the 3 standard deviations. So basically it's saying we are going to have some outliers. We're going to have some extreme values on either end, on the high end and on the low end, but there's only going to be a few of them. The majority should be around the average. And you can think of that as like kind of test marks. Yes, you're going to have people that are above the average, but not many. Right? You're going to have some people that are below the average very far, but as you get closer and closer to the average, you should find more and more people, or more and more of your data values, or more and more of the marks should be around that average. So there is a video to calculate standard deviation by hand. We are going to walk through that together, but if you'd rather watch kind of a cartoon video on it, you can always check the one in the online content. So first, right, the first example, the following data represents the number of home runs in a season by players on a team, and we want to find the standard deviation. So when calculating by hand, it does help to create a table to organize our calculations. Now the calculations aren't difficult, but they are tedious. So what we want to do first is we want to find the average distance from the mean, so from each data point, right? So each data point, we want to find out how far they are from the mean. So the first thing we need to do is we need to calculate the mean. Right? So we need to go through and add up all our values. In this case, let's call it the population mean. Right? We're looking at everyone that's on the team that's hitting a baseball or hitting home runs. So we're going to add up 3 plus 10 plus 0 plus 12 plus 5 plus 6 plus 10 plus 16 plus 34 plus 11. And then we're going to divide all of that by 10, because we have 10 values, 10 data points. And we should find that the mean then is, I believe, 10.7. So our average is 10.7. So now we want to find the distance, right? We want to find the distance between the two. So if we take our value, 3 minus 10.7, we get negative 7.7. And we're going to go through and do the same thing for every value. 10, or our data point, minus the average, so negative 0.7. 0 minus 10.7 equals negative 10.7. And we just continue down the list, do the same thing. 12 minus 10.7 is 1.3, negative 5.7, negative 4.7, negative 0.7. 5.3, 23.3, and 0.3. Now our formula tells us that we have to add up all of those values. Right? If we want to add up all those values and divide by 10, if we want to find the average distance, right? If we add up all these values, we find that they equal 0. And you divide by 0, then that's 0. Or we divide by 10, that's 0. So 0 divided by 10 is 0. Right? So we find that it doesn't give us an actual distance. And you're going to find that always happens. So what we have to do then is we now have to square the deviations to prevent the positives from canceling out with the negatives. Right? So if we go through and square each value, we'll get rid of the negatives, so everything will be a positive number. Right? So what we need to do then is we need to square each value. So negative 7.7 squared equals 59.29. Negative 0.7 squared is 0.49. Negative 10.7 squared equals 114.49, and so on. We can continue down. So you're squaring all the values in the previous column. Oops. 28.09. So you can see that it's not a hard calculation so far. Nothing's too difficult that we're doing. It's just very tedious and just remembering the steps. One thing to note, that this entire column should all be positive numbers. Right? That's the reason we're squaring it. We should get all positive numbers. Right? So if you're getting negatives, then chances are you're not putting brackets around it, because when you square a negative number, you should get a positive number. However, if you don't put brackets around it, your calculator might not include that negative and square the number and leave the negative out front. So don't forget, we do need to find the average distance. So all we did was get rid of those negatives, but we still need to find the average distance. So we need to add up all of the values, which we just did. We get 802. We then divide by 10, the number of numbers, and we get 80.21. So that is the average of our yellow column. So that's the average of the squared distances, right? So to undo the fact that we squared our numbers, we need to then square root that final answer. So then that means the average distance from the mean is 8.956, or 8.9, you could say. So that means within one standard deviation from the mean, right, so each data point is plus or minus roughly 8.96 or 9 units away from the mean. Right, so if we think of our mean as being 10.7 plus or minus 8.96, so that means that 64% of the data should fall between this interval. That's essentially what the standard deviation is telling us. Now, if it's a large standard deviation, then that means that the data is spread out. If it's a smaller standard deviation, that means that things are closer together. Now, you do have to, you don't really need to take into account how large the values are, because you are subtracting it or finding the distance from the mean. Now, sometimes if we are using large values, like maybe we're looking at population, things like that, where the numbers are very, very big, you might have a larger standard deviation based off of that. So you do have to also keep in mind what the data is that you're using to calculate. In our case, most of our values were around 10 and 11. Right? We did have that one value of 34 that did basically cause our standard deviation to be large. Right? So that is why this value is quite large in terms of the standard deviation. So again, now we want to go through and basically go through and do the same thing. Right? We want to determine the standard deviation of the following students' ages, and we're going to show our work just to kind of get used to calculating this by hand. Right? So we have all the values. I've gone through and I've put it into a table here so we can start to go through and basically do the same thing. We do need to calculate our average first. And I've already put it into order to help me kind of figure that out. So I'm going to calculate my average, or mu. So we can say 14 times 2, because there's 2 of them, plus 15 times 3, plus 16 times 4, plus 17 times 2, 4, 6, plus 18 times 2, 4, plus 19. All divided by, I believe there are 20, so it's 5, 10, yep. All divided by 20. So when we go through and calculate this, give me 1 second to type this in, because it's not necessarily the easiest. So we do get an average of 16.5. Now the nice thing about having a lot of values that are all the same is that when we go through and do this, so 14 minus 16.5, we get negative 2.5. That means that these two are going to be the same. Same thing for the next one. 15 minus 16.5, get negative 1.5. So it does help, it does make the calculations a little bit quicker, even though there's more numbers. again, the first column is going to be the distance from each value is from the mean. So 17 minus 16.5. Minus 16.5. And then 19 minus 16.5. Same thing for the next one, right? When we're calculating the squared of each distance to get rid of the negatives. Might seem tedious at first, but the fact that we can just copy the same value down does make it a little bit easier. And the nice thing about the negatives is that it's going to be the same value as the positives. Because when we square a negative number, it'll be the same as if we squared the positive version of it. So we can quickly go through a little bit faster. So again, these are all the squared values of the previous column. Again, not a difficult calculation once you get the steps down. It's just very tedious. You can imagine if you had more than 20 values. That's why it's nice that we do have Excel and Google Sheets that will do this calculation for us, which we'll look at later. But it doesn't hurt to learn it by hand and kind of appreciate the technology then that goes into calculating this for us. So now that we've added or we found the squared distance between each point and the mean, now we want to add all of that up. We want to find the sum of each value minus the mean squared. So I'm just going to use some technology quickly to go through, add up all those values so that it is quicker. So we add them all up, we get a sum of 71. Now we have to divide that, find the average by how many we have. So 71 divided by 20 equals 3.55. Technically, that is the variance. Right, we talked about those two formulas. So before we square root our answer, we actually have our variance. But again, it doesn't help us too much in terms of figuring out the distance from each point because we squared it. So then we take the square root of that value, 3.55. And we get a value of 1.88. So therefore, standard deviation is 1.88. That means on average, each data point or each datum is plus or minus 1.88 units away from the mean. So on average, that's what or how far each point is away. And again, so this is relatively smaller now compared to the last one, right? So we can see that the data is mostly close together. And if we think of the average as being 1 or 16.5, that means most of the data, or 64% of the data, falls between roughly, say, 18.3 and 14.7. Right? So that's where most of the data falls. 64% of the data falls within that range. Now, in some cases, right, we might be dealing with sample standard deviation, right, or sample means, right? Samples rarely contain extreme values when compared to entire populations, right? Sample is a little bit smaller. We're not collecting as much data. When you look at everyone in the population, you might find more of those outliers, more of those extreme values by comparison. So because of this, the standard deviation is often less than expected, right, when we're dealing with samples because we don't have those extreme values, right? So by dividing by n minus 1 instead of n, right, when we're doing our calculation, it slightly increases its value. So it's kind of the mathematical way of accounting for the bias that might occur because you don't have those extreme values when you go through and do the calculations. Right, so we're going to do the same thing. We're going to go and work through and calculate the standard deviation of the following sample. Right, so that is key. We want to find the standard deviation of the sample. Now we still need to find our mean. That doesn't change. Right? We still need to find, in this case, our x bar because it is the mean now. So when we add up all the values, 2.11 plus 2.02 plus 2.10, 1.99, 1.92, 0.01, we end up with 16 divided by 1, 2, 3, 4, 5, 6, 7, 8. Divided by 8, we get an average of 2. So I'm going to take each of our values, I'm going to place them in the column just to organize it. Again, the order doesn't matter in this case, so it's not like the median where you had to organize everything. I think I have missing 1, 2, 3, 4, 5, 6, 7. Yeah, missing 1 column. That's okay. Go through. Now I'm going to do each value minus the mean. One minus 2. Again, tedious. Nothing's really changing so far in terms of the actual calculations from what we've done before. It's just the one step that we have to do at the end that will change, right? That division at the end. So finally, then our next one, again, now we're taking all these values that we just calculated, those differences, and we're squaring them. So this one I'm going to use technology just to kind of speed things up a little bit. So I've now squared all my values. So the next step that I need to do is find the sum or add them all up. So the sum of each value minus the mean squared. So basically every number in that column that we just calculated. And again, I'm going to quickly speed this up. So we add all of those values up. We add that column up and get 0.0428. And then we do have to divide. We do have to divide now. Normally we divide by n, the number there are, right? To find the average. But because we're dealing with a sample, we're going to divide by n minus 1. In this case, 8 minus 1, or 0.428 divided by 7, which gives us a value of 0.0061. So this, again, this is our variance. Doesn't really help us too much. But once we find the variance, we square root it. That should be the last step. We square root our answer, and we end up with 0.078. This is our S, or our standard deviation. So, tedious calculation. Slightly different when we're dealing with sample or population, so we want to make sure that we're clear on which one's which and what the question is asking for. It doesn't change much except for this one step when we're dividing. Right? Instead of dividing by the number of numbers to find the average, we divide by n minus 1, or the number of values minus 1. Now again, because it is a tedious calculation, it might be like, okay, if I have a large set of data, large numbers, not going to be the easiest thing to calculate. There are ways that we can do it using Google Sheets or Excel. Right? So there are two formulas. One looking at range, right? Find the max and then subtract the min from it. So slightly using two parts in our formula. And then for standard deviation and sample standard deviation, it is relatively straightforward. You're typing in equal, and then st dev, and then p for population, or just without p for sample, and you're highlighting your data to fill in those brackets. Then you hit enter, and it gathers all the values for us, or calculates it for us. And we'll look at that later. We will go through a short lesson later that goes through those values, goes through those calculations for us. So again, one of the measures of spread that we looked at, the main one, standard deviation, we just looked at calculating by hand. Again, it is tedious, but it isn't too bad, right? As long as you make that table to kind of organize your calculations, organize your thinking. And don't forget, there are two different formulas depending on whether you're looking at the sample or whether you're looking at a population.